Okay, so welcome to lecture 17. So we had left ourselves with a homework problem, which was to study the subgradient descent convergence. I put the proofs, as I said, I'm not going to spend the time in the class, but it'll be useful to understand salient elements, right? We saw our journey from 1 upon epsilon square to log of 1 upon epsilon, and then we tried to do course correction 1 upon root epsilon um, for the case of acceleration we were able to get when we have smooth functions and just convexity. Okay, so this was an achievement for us, but we are in for a bit of an anticlimax here. When we do subgradient descent as a generalization of gradient descent, so for diminishing step size, so this was a kind of something I gave you for reading, the claim that if you look at the best iterate, okay, by the way, we used best iterate because we are no longer assured that it's a descent algorithm. Okay, so let me put that note there. So best because we are no longer guaranteed descent. So look at the best iterate so far from the T updates we have done so far, and you can have these step sizes either fixed or diminishing. The fixed size is not very interesting, as we all agreed upon. Diminishing was somewhat, there seems to be some convergence, which is f of xt best is less than equal to f of x star, plus there's an additive part which is diminishing with square root t. Okay, so this is the proof procedure. Just invoke the definition of subgradient method. What is a subgradient? That which lower bounds in a tight manner or creates a supporting hyperplane, in other words, to the epigraph. Okay, so this is the supporting hyperplane to the epigraph. Okay, I showed this to be differentiable, but you can have it non-differentiable as well. Okay, and this is fine. And then we said if we add this inequality across all the epochs 0 to t, we'll not overdo this battle of t, whether it's t or t plus 1. Right, so they'll say 0 to t, we do that. You'll have x of t plus 1 minus x star square is less than or equal to xt minus x star square, and this component here, right, adding across all. Now what's happened? What has got cancelled out? Has anything got cancelled out here? Sorry? Yeah, the terms, which terms to cancel out?
The norm terms.
This term, xt plus 1 minus x star. Sorry, should not be?
It should not be additional minus on the left hand side. Minus. It should not be minus xt.
This should not be minus.
Because the equation will be wrong. It should not be minus.
So this is you're saying plus.
It should be plus.
Okay. Does that disturb things? So wait a second. So else f of x star is a it is minus.
No, no. That will be plus there, but in the equation above we have xt minus x star.
Huh.
Here we have x star minus x, so it will not change, it will just be.
Oh, sorry. Yeah, this is xt minus x star. Right. Okay. Yeah. So we are fine. I think this was a small correction. Right. So when you use this inequality, then you'll basically get all terms cancelling out except for t plus 1 remaining on the left hand side, t on the right hand side. So what else? As usual, we can make an assumption that the first iterators within a ball radius are x1, x0, whatever, right? So, or rather x star. Okay, so something like that. Okay, and the other thing we notice, yeah, so that r square we use anyways is r. But the other thing we notice that the left hand side is also greater than equal to 0. The other thing we can make use of, if you want Lipschitz continuity to be invoked, is with respect to st square, norm of st square. Lipschitz continuity, not smoothness, right? So that is also possible. This is less than equal to L square. Well, it's less than equal to gamma t square L square. Okay, this specifically is less than equal to L square. Okay, so with that, what happened? Okay, so with that, we get this expression L square, R square. So we all seem to be set. This part in yellow is now bringing to fore the reason why we have any condition on gamma t at all, right? So what would we like on gamma t? I think we should discuss that here, right? What conditions do you like on gamma t? I mean, would you like gamma t to go to 0 as t tends to infinity, for example? See, we want to make sure that, okay, we have made this transition here, that the summation over gamma t f x t minus f of x star is less than equal to r square plus this additional term. Now we will translate that to f t best. So that also will hold, right? Because this is anyways less than equal to. Okay, so what would we like the gamma t to behave like? Any thoughts? I mean, what happens now if gamma t is constant? That's what we showed earlier. May not be most satisfactory, but what happens? We'll have this, this is, we'll have basically sum of the gammas here and then gamma square here, right? So you'll have f of x t best minus f of x star is less than equal to r square by 2t gamma plus t, oh sorry, the t will get cancelled, right? Plus gamma L square, something like this. That's what we saw. Huh? Why would we have a gamma? Well, you'll have this also summed up t times, and this also summed up t times. By 2 you're saying? 2, not t. Okay, so now r square, now what about this term? R square plus L square gamma square t by 2 d gamma. So as t tends to infinity, then it just tends to L square gamma by 2. That's what we saw earlier. But for diminishing step size, what do you get? So, okay, what is notion of diminishing here? So certainly gamma t goes to 0 as t tends to infinity. But what more? So sum of squared, what would you like to happen? L square can obviously be taken outside. That should be? You would like some of the L squares to be finite. Right, so. Sorry? Right. Ideally. Okay, so certainly you want summation over gamma t square to be finite. What more? Sum y should be infinity. So let's actually write down the expression. Okay, good. So yeah, we have to write down the expression properly. So we'll have to take f of x t best minus f of x star. Right. So this entire thing will go to the right to summation gamma. So that becomes important. R square plus L square summation gamma t square. Okay, so what we want is that this denominator, I mean, we don't want it to remain finite. So this, so let there are two parts here. One is this gamma t square is less than infinity, that is this part, summation gamma t square. And the other part is we want this summation to go to infinity. Okay, now you see why those conditions were required. So what will happen to this? This is finite, the denominator becomes infinite, this goes to 0 as t tends to infinity. Is that clear? So what's an example of gamma t square going to 0? Summation gamma t square. Sorry? 1 upon t square. 1 upon t. Huh? So you're saying gamma t equals 1 by t. Any 1 by? Sublinear term will also work. So what are the sublinear terms you could think of? Okay, great. Okay, so I've taken this one example. So I've taken R divided by L just so that some of these also get cancelled, but that's okay. But important to note just the 1 upon root t. Okay, so then the tendency we obtain is what? Let's write down the full expression. What's the full expression? Sorry. Thanks for pointing out. This is small t. With gamma t is r by L square root t. What do you get? So if we say I want to get f of x t best minus f of x star is less than equal to epsilon, requires how many iterations? T to be greater than equal to what? Yeah. So we want this to be less than equal to epsilon. What's a sufficient condition? R into L by root t, something of that sort, right? So if all you need to make sure is that the right hand side divided by this summation is less than equal to. So let's write that. Okay. Sorry. So you would need that this expression is less than equal to okay, what does it require? What does it require of this term? This should be less than equal to epsilon. And when is that going to happen? Yes. How do you work it out? So, sorry, we can't get a closed form. But what will be that term like? Sorry, can we maximize the left hand side? With respect to capital T. So what happens? That's a good point. So what will you get then? Should you maximize, minimize? Again, there's a question. Okay, those on the call could also suggest here. What would you do? Could any kind of expansion help you? We just need an idea of the dominating term. Sorry? Okay. So you'll maximize the left hand side is what you're suggesting then. You're saying the denominator should be as small as possible here. By the way, numerator is diminishing slower than, faster than denominator anyways. The numerator in the sense the non-fixed term. R square obviously is fixed. But this is diminishing fast. The part in blue is diminishing slower. Yeah. Try and work it out.
We are always giving we are moving in the slowest possible way. We say that let us equate all gamma small t to be r by t into capital T.
So you're saying that instead of, there was a purpose I put this capital T, right? So you're saying, okay, let's take gamma t to be the worst case r by 1 L square root capital T. Huh? Okay. So that gives what bound?
That we are moving in the slowest possible way. And moving to the slowest possible way gives certain more than any speed up will obviously give us.
So what does that give you? What? Huh? Okay. So instead of saying maximizing by, then it's not exactly maximizing with respect to t. I mean, the spirit is the same, right? The spirit is that you take the smallest value of gamma t is r upon L square root t, which is what I had written earlier. I jumped some steps, right? So suppose we have that, right? The smallest value. Then what happens? We'll get 1 upon 2 t times, you'll have 2 r square root t by L, something like this. L r square plus L square, and this will be simply r square by L square. Which implies that, okay, so now a whole bunch of things will get cancelled out. Any other L will get cancelled out? No, right? Okay, sorry. This r square will get cancelled out. You'll get you'll get square root t is greater than equal to L upon 2 epsilon sorry
R into L by square root t is less than or equal to.
So this sorry
RL by square root t less than equal to epsilon.
no, the second term will remain, right?
No, R square cancels out, so only 2R square is remaining. So 2R cancels.
Yeah, but it's an addition. Wait a second. Oh, sorry. I made a mistake here. Okay. Thanks. There's some. Yeah, this is the problem with trying to take shortcuts. Okay. So this. Yeah. Okay, thanks. So this is, so you'll have R plus R2R and then L upon L upon, so this 2 will also get cancelled out obviously. So L upon into R is less than equal to epsilon. So basically you'll need T which is greater than equal to L square R square by epsilon square. Okay, so this basically amounts to saying that T is omega 1 upon epsilon square. Okay, for all the hard work. Now, is this something we are happy about? I mean, we had to work really hard to get so far. But is this something we are happy about? Huh? Hmm. 1 by epsilon square. So like 0.01, then you would require too many iterations actually. So yeah, this is what we got. Right. So Lipschitz continuous functions, we had earlier got R square, V square, epsilon square. We got exactly the same. Right? And the subgradient, yeah, no surprise at all. The only thing is, there we were able to do somewhat, we didn't talk about step size so much. We had to analyze, we need more assumptions on the step size. That's important. Okay, so I'll just make that note. Subgradient requires similar but with more assumptions on gamma. Okay, so that okay, that's a summary. And the proof methodology was also different, by the way. We could not talk about descent. So in fact, there are many differences. We should write them down so that it is registered. These are more important than the actual proofs, right? So this is one. The second assumption is we could not use descent at every step. We use the best iterate. So subgradient descent analysis is in terms of this best iterate. So I'm not even, so I just descent, it's, sometimes we are embarrassed to say descent. I mean, it's not guaranteed that you're descending. Okay, great. So these are the two steps. So now we'll move on to more specific, things we can do for machine learning. So certainly, subgradient descent would never come up in a general optimization discussion. So that's specific. While subgradient descent is specific to machine learning, somewhat specific, it can be even more specific. Well, I must tell you that Lipschitz continuity issued smoothness also a lot of analysis has developed because of machine learning. Um, so a lot of analysis based on Lipschitz smoothness. and continuity can we be even more specific? Oh, machine learning. Okay. So the thing we note is what? Machine learning, what do the loss functions? You probably have a hint from all of these examples. What strikes you in all of these? Does this strike you somewhere? The summation component? Summation overall examples. Right? So the summation overall examples should strike you. Now, are these examples all very different? Okay, if I give you a typical data set, classification data set, would you expect every example to contribute equally? So let's say classification I have these are positive and then these are negative. Right, and you can try and happily come up with the separation. But you realize that some examples matter more than others. So which examples matter more? Well, the positive case maybe these examples matter more. For the negative, maybe these examples matter more. So why should we sweat it out on all examples? Okay, in fact, I will be motivating subset selection later on when we do some modular optimization very soon. Also from this itself. So I'll say that there's a subset that might matter more. In general, a subset of the data points might matter more. What is that subset is an interesting thing to identify. So I would like a little brainstorming here. What would you like that subset to be? Instead of the summation over all examples, what would be that subset that would make the difference? Okay, so sorry. Okay, so let's write down. Good point. So this you're talking about maximum magnitude is like so maybe high uncertainty associated with those. That's a measure of uncertainty, right? So let's just reproduce this on the next slide. So question, which subset of data points might matter more? Okay, I'll be actually using this slide later on again. So I want input from all of you. One suggestion was perhaps points close to the boundary. Well, I don't know what are points close to the boundary because that's a chicken and egg problem, right? But here is a chicken and egg problem. To find the boundary, we need to learn the model. So who gives you the boundary? So you may say, oh, current boundary. Right? Possibly current flaky boundary. I mean, it's changing, it's evolving. Flaky, evolving boundary. Okay, so that's possibility, right? I mean, the orientation could change, fine, then my semantics of boundary points will change. If it becomes like this, some other points become, if it becomes like this, some other points become. So fine, I'll live with it. What else? That's one. The second suggestion that came up was points with high gradient. Very interesting. Again, I mean, all this will have the same issue. Question is, what is less flaky? Points with high gradient, with the understanding that, I mean, when you say high gradient, I mean high gradient magnitude. Right. So with the understanding that gradient norm is the uncertainty. Why do you say that? Why do you say that? So, sorry, for those on the call, the suggestion is points which are very far away from the boundary will have high gradient. Sorry? We should not use them in the subset. Yeah, so what is the meaning of high gradient? Again, my question to you.
So the function changes drastically at that point?
So there's another suggestion, function changes drastically at that point. Okay, so that is interesting. Since the short distance, let us write commands. Function drastically at points, which right is high. So if I, it's very kind of uncertain. What's another suggestion? Okay, points which are at the shortest distance from the points of the opposite class. Okay, I mean, each of this is interesting. So you're basically saying that the points which are far away from the opposite class are what? I mean, they're well already satisfied. Okay, so they won't be very critical to determine the boundary, and hence won't be critical to determine. Sorry. I mean, hence is not required, and won't be critical to determine the boundary. And so, as your, let me just tell you each of these, right? Points close to the boundary which you're trying to select. This is the general idea of core sets. Okay, I'll just write down these names. Core set. Since I said we'll be moving to subset selection, so core set based approaches. They have this, but I'll look at more specific. So gradient norm. There's a lot of so this is reference. I'm just refer. The second class which you talked about. Again, there are a lot of curriculum-based approaches. So what they do is they have a curriculum which iterate over points and then look at gradients with high magnitude. Of course, now I mean, initially you may do that, but eventually you'll say, okay, these are uncertain. Let's forget them. Right? So a third, there is this algorithm called crust. Okay, I hope maybe sometime we'll talk about it. But what crust says is that, okay, I will, for each class, I'll identify the canonical points, right? So I'll identify the representative points for that class and use only those points. And basically, the non-representative points for each class are like the noise points. Okay. So crust is an so this is a reference. Crust. I think this was ICML or NeurIPS. I don't remember, but 2019, which identifies noisy data points in each class, or rather identifies representative data points.
If we get those noisy points correct, then you are looking
Right. So what it does is it gets this representative data points using something called k-medoid clustering. Okay, and now it can do based on gradients. So there have been variants there. Can be in feature space. You can do it in feature space. You can do the clustering in feature space, or in gradient space. Since now you're already motivated, gradient has a lot of information. Right. So there are a lot of algorithms which do gradient space. In fact, there's an algorithm called Craig. I'm just writing. Craig is ICML. Or as in Craig in, and this is I think ICML 2020, which computes. Yeah. Oh God, what did I do? Something wrong. Okay, so something went wrong. Or as in, sorry, I'll have to type again. Too long is preferred. Yeah, or as in Craig in ICML 2020, which computes, yeah, gradients, computes k-medoid clusters in gradient space, so that remaining points are noisy points. Okay, and now it not only that, I mean, such clustering is done in each class. So in each class you will find this, because the training data you have the labels, you can do that. So that's how it tries to do away with the chicken and egg problem. There is still a chicken and egg problem because you're still, the gradients will change, but at least I'm using the class labels. Okay, so good. So refer crust. Crust is I think in NeurIPS 2019. Okay. Okay, so these are some points. Is there any other thought on how the subset of points would be selected that matter more?
So with the X space of X, we can draw a small ball around all the points, and those who have more neighbors, as we said, will be less important, and those who have fewer neighbors will be more important.
So draw a ball around each point and look at the neighborhood, and if there are too many neighbors, it's like crowded, then it's important.
Then it's not important.
Oh, neighbors from the same class, you mean? Okay. I mean, in some sense, what you're doing is taken care of here, but like good point that you made. So what he's saying is exactly what these would be doing. So let's look at these, right? Positive points are there, and that's why you're doing k-medoid. Let's say these are negative points. Okay, now these negative points may also have clusters. Positive may have clusters. And there could be some stray positive points and some stray negative points. Now, without any regard for the boundary, which we were trying to do earlier, You're saying, okay, I'm just looking at gradients and then I'll try and find the cluster centroids, so to speak. The goal is to eliminate. I mean, yeah, not exactly what you're saying. So what you're suggesting is slightly different. You're saying you only pick some points. Here they say that you'll reject these points. These are rejected. These are because they're outliers. I mean, they're outliers in the sense they're in silos. But you could go further and say, oh, I will use these cluster centroids in a different way. If there are too many points around a cluster centroid, I'll not pick that point. So there are multiple approaches. Now, I think they are talking about the same thing, using it differently, right? So manifold, you're looking at the manifold. So in fact, Crust has this very interesting, sorry for interrupting you, but Crust, what it does, it says, okay, let me just give you an idea. So Crust looks at the Jacobian. Now, Jacobian, right? Basically the gradients all stacked together. This is what Crust does. So what is Jacobian J? It's all the gradients stacked together. F of x1, f of x2. Okay, I might be wrong in the reference, but I'll put it correctly afterwards. So this it says that's the original intent, though eventually they just do clustering. But the original intent in Crust is that you take this Jacobian and decompose it into a noise space and information space. So noise and information is in the gradient space, as you can see. Okay, so Crust. So I'll just write down what Crust does. Crust intends to decompose the Jacobian into a. So basically think of eigenvector decomposition, right? So find the principal eigenvalues that will correspond to the noise space. So it's a linear transformation of the set of gradients. So you're going beyond a single gradient. So far we are saying, okay, find the highest magnitude individual gradients. But here we are having a macro view. Through eigenvector decomposition to get a macro view. Okay, so it intends to do that, but yeah, it eventually lands up just doing this clustering. Great. Are there any other thoughts? We can do kernel computation, non-linear kernel computation, and then in the kernel space again. Okay, we'll be doing, okay, that's interesting. So we could use some kernel function to find similarity. Even in the gradient space, you can find similarity of points. You can do polynomial kernels in the gradient space. In fact, I'll be talking about our library called submodlib. I mean, you've probably seen submodlib has those, right? So we allow for computing gradients and then kernels on those. And even with those, we can have different, we can have graph cut, which has a different notion of representation. And then there's DPP, which does diversity. So that's a good point. So let me add that as well. So such clustering subset selection can also be computed on kernel functions. Yeah, so see submodlib, which I'll be talking about very soon. Okay, great. I think this was very useful discussion. I'll revisit this slide. But now we're going to start with something very simple. What's the simplest? All this is very nice, but what's the simplest you could do? I mean, this is all quite sophisticated, right? It's saying, okay, I'm going to take gradients, look at the noise, look at the information, do clustering, a lot of work, right? Work is there. I'm not saying that's not worth it. It's worth it. In fact, I'll talk about our work on match and we have blister approaches. That match is actually totally based out of gradient computation, right? So there's a lot of value. Let me give you an idea what grad match does, right? So what is happening? Yeah, actually we have this grad match as well, where we say, so that's, let me take the example of grad match. We say I want a subset min over the subset of the data points x. Let's say training data points, such that the sum, I mean, there's also min over w. Okay, so I'll look at the weights also. You can also weights of gradients. Weight on the loss on the xi component, such that this weighted sum of gradients best approximates the full training gradient. Call it LT. So here you say I want a subset of points and the weights of the gradient such that this weighted sum is best approximating the entire training gradient. So this is all nice, and there are, we'll talk about how we can do this efficiently. But on the face of it, all this looks very computationally intensive. You'll have to do some more work, unless we learn good tricks of sum modular maximization and so on, right? So what would be a poor man's start?
Just when you create every point, maybe created at any particular point is very fast or values are zero. And just skip those particular instructed description on those particular coordinates and update the rest.
Okay, yeah, but all of this will require gradient computation overall. Can I suggest that we could?
Hello.
Yeah, somebody was saying something.
Yeah, sir. For a start, we can just select the random data points, right?
Okay, there's a suggestion for a start. Why just not select a random subset? Right? I mean, why will a random subset work? I mean, the basis of why a random subset work is pretty much what we have been discussing. What is the logic behind a random subset working? Anyone?
We have enough data points and it will be representing the whole data.
Yes, so we have enough data points, and all the above approaches are trying to look at redundancy. So if there's so much redundancy, why not just pick a random subset of points? And I'm telling you, random is not a difficult baseline to beat. Okay, so it might look, especially if you do random, if the random subset is random every epoch, it's quite difficult. We call it random online. It's a hard baseline to beat. So you have to work hard to beat it basically. Okay, so thanks. Yeah. So let's look at so simple and strong start. Since above approaches leverage data redundancy, why not pick a random subset of points? Okay, that's the strong start, sometimes hard baseline to beat as well. Okay, so there's a suggestion that if the number of points in the boundary are not very less, you will anyways pick those up as part of the random scheme. So yeah. Okay, so with that in mind, let's look at the framework of loss functions. So as I said, they look at this large number of components. Fi is a cost function of the ith observation, and so on. And the issue is, as I said, this is in computing the full gradient. This order and computation. But not only that, it also is redundant. So we are okay with this overhead if it was completely worth it. Moreover, it is redundant. Okay, so I'll be using some slightly different indices because we are moving to the stochastic space. I is an index into the example, and W is representing the function parameter. So I will not use X, I'll use W, weights. And T is an index into the iteration. Okay, so let's now move a little fast with this understanding. The simplest, the simple scheme which we wrote in the red, right? So I'll just copy this part. So to recap this simple and strong. Yeah, so the previous approaches, we are trying to take the best lesson out of those. So for times t equals 0 to capital T with step sizes. Now step sizes start becoming very important if you are looking at subgradient, and also with stochastic they are important. We also saw how in the previous class, right, through some collab notebook exercises, we saw how some of the accelerated versions, the momentum versions in some sense, are also giving a different perspective into the choice of the step size. But of course, they have an additional direction momentum also. So what you do is you start with some initial weight, sample I in n uniformly at random. Okay, this is the simple scheme. And then you compute the gradient vector or subgradient vector. And sometimes we'll even drop the index I, call it just GT, because we're looking at some random point. We don't know what that random point is, right? I is in random index. And then you'll update only with a gradient of Fix. It's a full gradient. So at the outset, this is by design n times cheaper than full gradient descent. Okay, but let's do some, get some more insight. So now there is inherently, right, because we are now doing, look at this, we are uniformly at random. Okay, uniformly at random gives you something called unbiasedness, and I would like you to help me complete this. Right, and in theory, most of the times you're assuming that it's uniformly at random with replacement or without replacement. What do you think? Huh? With replacement. Now, if you have to do without replacement, I mean, that's a lot of bookkeeping. Right? I'll need to keep track of all the points I picked so far. I have to look up that, like heaps, right? I have to look it up and then come back and say, well, don't pick it, pick another point. So, uniformly at random without replacement, with replacement is default. Yeah, and in practice, of course, what do you do? Would you like to do with replacement or without replacement? So in practice, you do with replacement or without, and question is, in theory, is it with replacement or without? In theory, it's without replacement, and in practice, you do with replacement. Okay, so let's. I'll write down your suggestion. I'd like you to think a bit more. So with replacement is default in practice. That's what you're suggesting. Without replacement is default in theory. Yeah, I'm marking these as questions. Yeah, I think these go unnoticed. Typically, you're just users of optimization. You don't even pay attention, right? So give some thought to it. So let's do that. Okay, we have taken your point uniformly at random. So can we use convexity for vanilla analysis? What inequality holds in this expression consistently? Any suggestions? Okay, so left hand side is left hand side. So look at this, WT minus W star. It's a GT, by the way, not a G star, right? F of W star. So you have to look at it the other way. Don't get deceived, right? So what's if you're looking at GT, then what would you look at? F of W star is greater than or equal to F of WT plus GT transpose W star minus WT. So we have flipped things. So what would this be? What inequality would you have here? Okay. Okay, so now what happens if I do a summation? If I do a summation over T, oh sorry, T is what, yeah. So it should be a summation over I. I mean, this is for a single point. If I do a summation over I, let's say we call this Fi of the left hand side and do a summation over I of the right hand side. Will this hold? This holds, right? In summation as well. Okay, so answer is yes. Now the thing is, this may hold or may not hold depending on how the stochastic gradient GT turns out. Why? So the previous slide, say had we computed over the entire thing, we would have been sure. But now I've taken a point and I'm still looking at F over the entire set, right? The update is on a single point. Okay, so this is the complete loss, total loss, whereas GI is stochastic gradient. Is that clear? So does this hold for every point consistently? It holds for loss, for complete loss, if GT were complete gradient. Correct? But GT is not complete gradient. So therefore I have a question. Now will it hold? Is this clear? I can say that for the ith point, if I only compute the inequality at the ith point, then it's fine, right? So FIWT minus FIW star is less than equal to GTI transpose assume this holds exactly. This is a subgradient point, so obviously holds. Yeah. Okay. But if I were to just insert this GT, okay, I call it GTI if you want, just to be clear, right? I mean, when I'm assuming that GT is the ith points of gradient, whereas the F is the entire loss. That's what I'm looking at, right? So the part on below holds. Question is whether this holds. So, okay, may not hold since F is total loss, but GT is for ith point only. Is that clear? So that's the challenge we have. So it may hold or may not hold depending on how the stochastic gradient GT turns out to be. However, what is a saving grace is that this inequality holds in expectation. Okay, so in some sense that also helps. Like some of the analysis we'll do later on, we'll build on this when we do subset selection as well. But this holds because this GT is an unbiased estimate of FWT because we have picked the point completely at random, uniformly at random. Right, since point for computing GT was picked uniformly at random. Okay, so this the expected value of GT is basically the average value of the gradient, the sum of the gradients divided by n. Why did this hold? This one. Yeah. No, I made here if GT. So sorry, this is GTI. So let me just call this GT. Oh, so let's use a different name. So let's just call it GT bar. So this holds, right? GT bar transpose. This holds. So both of these hold. The one in red and the one in pink hold. Because here GT bar is complete loss, holds for complete loss if GT bar were complete gradient. Here GTI is admittedly only for the right point, and the loss here is also for the right point. Is that clear? So if you want, I can put a I index here also, just an I index. Yeah. Thanks for pointing out. But the GT bar is the complete gradient. Okay, can we proceed? So this holds. Okay, so that may not hold. I think let me just. That's a good point you raised. So I wrote this may not hold. What I meant by may not hold. Let me. Yeah, I understand the confusion. I've written this side by side. I'm just going to create one more write-up. So what may not hold, I'll write separately. In fact, let me. Thanks for pointing this out. This could have been potentially very confusing. This part is fine. And what I'm saying is may not hold is this expression. Okay, so f. Now I'm looking at the f, the complete f. Okay, so if you want, put a summation over I, fi wt minus fi w star. This I don't know whether it will hold if I, right, where now to take this gt as the gradient or subgradient, whatever, for the ith point alone. Is this clear? So this may not hold. I'm applying the function on all the points, but the gradient is only on the ith point. Is this clear? Yeah. So thanks for bringing it out. In a hurry, I just wrote down many points together. So this issue is because we are dealing with total loss, but we are dealing with stochastic gradient in pink. Now everything is clear, right? Yeah, in the green, we still are talking about stochastic gradient. This is still stochastic gradient, but then the function is also on that point only. Okay, so if you want, yeah, I'll put this in. This I'll just put in red. This is the one in pink and the one in green are both talking about individual points. Okay, this is function or loss. Is this clear now? GT bar is complete gradient. Okay, so GT bar is a gradient of f, the complete loss, or if you want, the gradient of the summation over all I points fi wt. Is this clear now? So that's where we say that inequality may hold an expectation. Okay, what's the time? We have some time. Okay, so now coming to the convergence result. Any questions? Let me know. Those on the call as well. If you have questions, let me know. Okay, so now the step size we'll start doing magic. Okay, so hereafter convergence results are not going to be easy, and sometimes we have to do assumptions. I mean, it's sometimes very difficult to apply all those Goldstein and RMO condition 1, 2, 3, 4 show under those assumptions it holds. It's not easy always. After a point, it just becomes more of best practices. Though in the simpler cases, we could prove in all conditions. Okay, as I said, my additional notes I have proofs under different conditions as well. But here you will start finding some black magic coming in. So what's the black magic here? Choosing this constant, we say constant with respect to square root t here. Okay? If you choose the step size, and if it's f is convex and differentiable with w star a global minimum, and w naught is within radius r of w star. And now we don't talk about Lipschitz continuity, but expectation, right? Or rather Lipschitz continuity in expectation. So that's a small twist. So I look at, in fact, when I present grad match, you'll find that there are many algorithms which don't require this Lipschitz continuity expectation. You may also sometimes use the full data gradient and try to approximate it, in which case you deal with the normal notion of Lipschitz continuity. Okay. But in this specific result, we are talking about Lipschitz continuity and expectation. So it's not that all variants we'll talk about will only hereafter subscribe to Lipschitz continuity expectation. This is one variant. Okay, so now what with all of this, what happens? I mean, this looks very close to what we did for subgradient descent, right? In fact, we had 1 upon square root t, small t, and then we said, okay, the smallest you can take is 1 upon square root t, right? So recall this choice. So this is motivated from subgradient descent. Okay, so now what does it look like? It says that in expectation, if I look at now, the expectation is what? Of the f of wt, right? Because every wt was obtained using a point sample uniformly at random, its corresponding gradient. So the expectation of that update, a kind of stochastic update based function minus the actual function value, summed over all, is now less than or equal to rb by square root t. Again, it's like looking familiar. We had this. In which case did we have this? Sorry? Lipschitz continuity. So Lipschitz continuity, we had this all through. So things have not changed completely. Okay, so result similar to Lipschitz continuity for both gradient and subgradient descent, but of course in subgradient descent there were some slight changes. We had to keep track of the best iterate so far. We had some step size change specifications, but somehow we have managed, and we seem to be managing the same thing here. Now you can also talk about strong convexity. Again, a lot of this analysis we will not be doing. So if you have now a slightly different step size, okay, so the previous one was 1 upon square root t order, but now 1 upon nu, 2 upon nu into t plus 1, where we have mu as the strong convexity parameter. So now in expectation again, so the expectation of the function value, we'll talk about this soon, but in the function value basically now is less than equal to, the difference is in expectation less than equal to 2b square by mu t plus 1. So actually we didn't do subgradient descent, but it turns out in subgradient descent also you can get similar results. Now what is this? Can you help throw light on what this is doing here? F of 2 divided by t into t plus 1, t into wt. So there's this slightly different normalization. Yes, it's a weighted average, yes. So this entire expression can be viewed as what is that? 1 by summation into summation of t. Okay, so we are slightly different. We have basically an average, but weighted average. Okay, the weighted average. So the entire thing can be viewed as a weighted average. And that weighted average, by the way, is somewhat commensurate with the gamma t, right? Commensurate with the fact that we are scaling by 1 upon t, on order of 1 upon t term. So again, does this look familiar? Okay, by the way, b square, this b square is the max over all the t's of expectation. So does this look familiar for strong convexity? What did we get with strong convexity earlier? Huh? Sorry? It was similar. Here we are using Lipschitz continuity. So this is similar to convexity. Oh, sorry. Strong convexity plus Lipschitz continuity. So all this is assuring, as I said again, just with the additional stringent constraints on how the gammas are, their weighted combinations. In some weighted sense, it's converging, weighted average sense. Okay, so now let's just we'll do some comparison. How classical gradient descent is comparing against stochastic gradient descent. So just putting them side by side. So we had that norm, the gradient square was less than or equal to b square. So for sum of squares objective, then what's happening here? Oh, there's a norm missing, right? There's some norm missing here. This is, I think a norm is missing everywhere here. I don't know how that got missing. I don't know if the color has made it gone missing. Huh. Okay, so yeah, so now you see the parallel for upper bound b square SGD is now changed, right? Which is on expected squared norms of stochastic gradients. That's the only difference. But there is also some correction. So one is to say, okay, there's a difference, you've just replaced. There is this Jensen's inequality, which is basically the convex inequality. What's the Jensen's inequality for, when we say Jensen's inequality for norm square, or what does that mean? That is, yeah, alpha W1 plus 1 minus alpha. So you can avoid the alpha if you want, just W1, W2 is less than or equal to. So the absolute value. Okay, assuming alpha is between 0 and 1. Okay, done. Why norm square? Normals. Norm is also convex. Yeah, actually it holds for norm square both. You put both. Okay, so now there is some correction between the gradient descents b square and the stochastic gradient descents b square. So you can show that the gradient descent b square, which is like the average of those, if you take the 1 upon an inside, right, basically this, yeah, this is the gradient descent b square is taking 1 upon an inside and then computing a gradient, right, gradient of the average loss. Whereas this is saying, sorry? Yeah, actually I should have written, yeah.
In the first class, instead of 50 norm,
Yeah, you're right. Okay. Yeah. In fact, all of these, yeah. Here, no? Thanks. Okay, so this is a Jensen's inequality, which says that the b square for gradient descent, I would expect it to be less than equal to b square for stochastic gradient descent. So I'm just, the b square for stochastic gradient descent is like a little bit more liberal, larger b basically. The more liberal Lipschitz continuity constant. Okay. Oh, we have already overshot. Any questions? We'll continue on this next time. In the next class, I would like you to just look at this. I'll post this, right? Get an idea of, subgradient convex, subgradient strongly convex, gradient convex, gradient strongly convex, right? In each of these cases, basically what's happening. Basically, oh, there's an omega here. Sorry, it's not. This one is an omega. Okay. So understand this landscape. So I would say this is an homework. Understand this landscape, but let it not just be, the analysis part. What are the practical implications of such results? And when you say practical implications, now we are saying like deep networks, deep learning. Assuming that we are dealing with the last layer, you probably still have some convexity on the last layer. But yet, what does this mean? Okay, we'll conclude on this. Any questions? Yeah, thanks. Bye.